Okay, welcome to section 5.4, discrete random variables and probability distributions. So what is a random variable? Well, it's a quantitative variable whose value depends on chance. For instance, the number of litters and the number of puppies in a litter. That's a quantitative variable, but it does depend on chance. The return of an investment, the lifetime of a battery. These are all random variables who are quantitative but depends on chance. Now what we're going to talk more specifically about are discrete random variables. Now discrete random variables usually involves a count of something where you can actually and physically count it. Okay? Where you can actually and physically count it. So, we have different kinds of notation for random variables that you're going to need to know. So the first kind that you're going to need to realize is that all lowercase letters represent variables. All the lowercase letters represent variables. Uppercase letters represent random variables. So for instance, if X is the number of siblings, okay, if I want to shorthandedly write 2 siblings, well, X, capital X, our random variable, equals 2, because these are randomly selected siblings, as you see in the definition of what X is. So X equals 2 would be our shorthand for our random variable notation. It also allows you to use this shorthand for probability. What's the probability of having 2 siblings? Well, the probability of that random variable equaling 2. It makes it a lot easier than having to write out that whole thing inside the probability parentheses. So the two main things that you're going to see with this section are going to be probability distribution and probability histograms. And basically what these are going to be is a probability distribution and histogram are basically going to tell you, they're going to show you the possible values and the likelihood that they're going to happen. So they're going to give you basically the probability that these things are going to happen and show it to you in 2 different forms. The distribution form, which will involve a t-chart, and the histogram form, which of course is a vertical is a picture illustration for us to be able to see the probability. Now it's important for you to note that with the histogram, we did relative frequency histograms earlier. This is going to be very similar to that, because remember, we can equate relative frequency to probability. So each of those bars, just like each of the bars represented relative frequency when we did that earlier in the semester, each of the bars here will represent probability instead of relative frequency. But again, it's 6 of one, half a dozen of another. So this is relative frequency and probability. Really, in theory, are very similarly defined. Okay, so, and you'll see what I mean by that here in just a moment. So, for example, we let X denote the number of siblings of a randomly selected student, and letter A, determine the probability distribution of random variable X. Alright, so notice over here we have relative frequency already done for every one of these. Every one of our siblings has a relative frequency. Well, what is probability? Think about what probability is. Probability is the outcomes you want over the total possible outcomes. Well, look here, we had 8 outcomes that were 0 divided by the total possible outcomes of 40 gives you 0.200 here, or 0.2. So this would be our relative frequency, but in the essence of this problem, it's also our probability. So you can equate relative frequency to probability, okay, with these particular problems. So if we're going to do a probability histogram, a probability distribution, which is what it's wanting us to do on this problem, first of all, let's make our t-chart. And so X represents the siblings, and the probability distribution would be written the probability of the random variable equaling X. So what is the probability that the random variable equals 0, 1, 2, 3, and 4? Because this is what our X represents. These are the different values of lowercase x. So what is the probability that x equals 0? Well, the probability that x equals 0 is 0.2. What is the probability that x equals 1? 425 thousandths. What is the probability that x equals 2? 275 thousandths. What is the probability that x equals 3? 0.075. And what is the probability that x equals 4? 0.025. So if you notice, these are exactly the same as the relative frequency. We just plug it in this called a probability distribution of the random variable x. So randomly selected, if x is randomly selected, lowercase x, what is the probability that the random variable will be? 0. What is the probability that the random variable will be? 3. And we have that listed. So this is the chart. This is letter A. So whenever something asks you for a probability distribution of a random variable, this is what I'm going to expect, okay? Some kind of t-chart, just like you see here. Pretty basic, pretty simple. The only way we could make this different is if we didn't give you the relative frequency. If we just gave you this column 2 right here, if we just gave you this column right here, all you would have to do is find the probability, which would be relatively easy. Just 8 divided by 40, 17 divided by 40, 11 divided by 40, and so on. And you would be able to get the probability like that. So that's another way you could see this particular problem. Alright, so B is to construct the histogram. Alright, so we have number of siblings on the x-axis, and we have the probability on the y-axis. And I'm going to use some rough estimates with this. I'm not going to get as specific as your book did. Okay, so because you can very easily turn to your book and see this same picture. Okay, so we have a break in our graph, and then we're just going to do 0, 1, 2, 3, 4. Okay, so if we're going to do the histogram here, what do we need to do? Well, we are going to look at where x is 0. What's the probability when x is 0? Well, it's 0.2. So I'm going to draw my bar up to 0.2. Okay, and that bar represents a probability of 0.2. Okay, that bar represents a probability of 0.2. Alright, what about what's the probability when x is 1? Well, it's 0.425. That should say 0.4. Alright, 0.425 is going to be somewhere up here. Excuse my shaky hand drawing here. And so here's the probability bar, histogram bar, that represents 0.425. Alright, 0.275 would be the probability when x is 2. 0.275 is going to be pretty close to 0.3 right here. 0.75 for 3 is pretty close to 0.1. And then 0.25. So here's our probability histogram, a rough drawing of it. Okay, and remember, each of these bars represents the probability. Each of these bars represents the probability. So when you're drawing a histogram, pretty basic. Okay, just be able to take that T-chart, convert it to a histogram. So that's probability distribution. All right, so let's look at this. Now here's what we just did, and here's the nice looking histogram, okay, that matches what I just drew. Alright, so notice what it says here. If each of these bars represents the probability, then the sum of all those bars should give you 1. That should make sense to you. If you have all the probabilities here, if you're looking right here, all these probabilities, if you add them up, you should get 1. Because remember, probabilities are essentially percents. So 20%, 42.5%, 27.5%, so on. If you know all the different probabilities, that should equal 100% at some point. So 100% as a decimal would just be 1. So all of these should add to give you 1. The same thing here. All of these bars, since they represent the probability, like this one's 0.2 and 0.425 and so on, you should be able to add up the value of all those bars and get 1 as well. Okay, so keep that in mind. That's something that we've done already. It's worded in a little bit different form here. Alright, so let's look at this example. And here's what it says. This is from the U.S. Census Survey, and this is the number of persons per occupied housing unit. This is a frequency distribution. So when X is 1, we have 27.9 million housing units that have one person living in them. We have 34.4 million units that have 2 people living in it, and 115.5 million units that have 4 people living in it. That's what this means. Now look at what it says down here. Let Y denote the number of persons living in the unit. Okay, so Y is the number of persons living in the unit. Identify the possible values of the random variable Y. So what could Y equal? Well, it could equal 1, 2, 3, 4, 5, 6, or 7. So Y could equal 1, 2, 3, 4, 5, 6, or 7. Those would be your random variables there. Okay? Well, look at letter B. Use random variable notation to represent a housing unit that has exactly 3 people living in it. Well, that's simply Y equals 3. That would be the notation of the random variable that has 3 people living in it. Okay? Y equals 3. And we could put that in squiggly brackets like that, where Y equals 3. Okay? So that would be how we write that particular one in random variable notation. Alright, well, let's look at letter C. It asks, what is the probability that Y equals 3? So what is that probability? And it says interpret in terms of percentages. Well, look at what we have above. We have frequencies. We don't have relative frequencies. So if you look at 3, 17 is not the probability. 17 is the frequency. So what we have to do is divide 17 by the total of all these frequencies, which would be 105.3 if you add all those up. If you add all those up, it's 105.3. So partial over total. That's what probability is. That's what relative frequency is. And so that gives you 0.161 is what that gives you. So what does that mean in terms of percentages? Well, what that means is this, that 16.1% of the houses in America have 3 people living in it. 16.1% of the houses have 3 people occupying it. That's what that basically means in terms of percentages. Okay, 16.1%. Alright, so let's look at letter D. Determine the probability distribution. Okay, so we want to determine the probability distribution of y. Well, we know that the y value here is going to be 1, 2, 3, 4, 5, 6, 7. That's the random variable side. Now, to do the probability, we have to do just like we did for letter C. We have to do that for every single one of these, okay? So you would go ahead and you would do 27.9 divided by 105.3, 34.4 divided by 105.3, and so on until you got all these probability distributions, which would look like this. And 4 would be 0.147, 5 would be 0.065, 6 would be 0.022, and 7 would be 0.013. Okay, so this would be your probability distribution. Now, to construct a histogram, I'm not actually going to draw this histogram on this example because we're running out of room here. But remember, you're going to make your histogram, label your values of y here, so 1 to 7 down here. Your probability will be on the y-axis, and then draw your histogram just like we did before, okay, in our last example. So that will, and remember, each of the bars represents those probabilities, so that when you add them all up, you get 1. All right, so that's that's one of our probability distribution examples. Hopefully that's pretty understandable for you. All right, well, let's look at another example. Okay, well, letter A. All right, so when a balanced dime is tossed 3 times, 8 equally likely outcomes are possible, and I've got them over here in table 510. For instance, HHT means that the first 2 tosses are heads and the third is tails. So let X denote the number of heads obtained in 3 tosses. Capital X, our random variable. Then X is a discrete random variable whose possible values are 0, 1, 2, and 3, because you can either have no heads tossed, 1 head tossed, 2 tossed, or 3 tossed. Okay, so letter A. Letter A. Use random variable notation to represent the event that exactly 2 heads are tossed. Well, to use the notation that exactly 2 heads are tossed, that's X equals 2. X equals 2. Alright, well, what about B? Determine the probability of X equaling 2. Well, go up here and count how many have 2 heads. Well, so you've got, you should have 3 that have 2 heads, sets of heads in them. 1, 2, 3. Right there, right there, right there. Those have 2 sets of heads in the first 3 tosses. So that should be 3 out of 8. So our probability is going to be 3 divided by 8, which equals 0.375. Okay, well, let's look at letter C. Find the probability distribution. Well, that should be fairly easy for this one because we only have 4 outcomes, 0, 1, 2, and 3, and they want us to find the probability distribution Alright, so what's the probability that we toss 0 heads? Well, there's only one up there, TTT, where it has 0 heads. And so 1 out of 8 gives us 0.125 for our probability. What about tossing 1 head? Well, you have 3 up there that only have 1 head tossed. So that's going to be 0.375. We already know 2. And there's only one that has exactly 3 heads tossed. And so that is 0.125. So there's your probability distribution of X. Okay? Not that bad, right? Hopefully not. Hopefully you're understanding, and this will be a fairly easy section for you. Alright, well, letter D. Use random variable notation to represent the event that at most 2 heads are tossed. Now here's where you've got to remember what at most means. What does at most mean? Well, it means it can be at most 2, but it can also be less than 2. So what at most means is less than or equal to 2. Less than or equal to 2. Alright, well, let's find the probability that X is less than or equal to 2. Well, think about what that means. That's the, what does that actually mean there? Well, that's the probability that X equals 0, because that's less than 2. That's the probability that X equals 1, because that's less than 2. And it's the probability that X equals 2, because it has the equal to bar under it, so it can be equal to 2. So you know all these probabilities from our probability distribution. So that's 0.125 plus 0.375 plus 0.375. So the probability that X is less than or equal to 2 is 0.875. Okay? Hopefully that's fairly understandable on how we got that. Alright, so interpreting a probability distribution. The main thing I want you to see here is that the word proportion and probability are when you start getting large numbers of observations, the proportion of time something occurs and will approximate the probability. Okay, so the proportion will approximate the probability when in large observations. So if you notice here, we had 1,000 observations. So our probability in our little 8 observation test that we did a moment ago is listed. Well, if you look on it to the left, the proportion of how it happened when we did 1,000 observations is almost exactly equal to our probability. So it is of our 8 outcomes that we just solved. So as you start getting larger and larger in number of observations, it starts equaling your probability. Okay, getting very close to it anyway. Alright, so this is section 5.4. If you have any questions, please feel free to ask your instructor, and we'll have section 5.5 here shortly.